Hello, everyone, and welcome. Today, we're going to tackle a chemical puzzle that, honestly, has some pretty profound implications for our health and the world around us. It's one of those concepts that, once you get it, it totally changes how you look at things, from medicine all the way to materials. So let's just jump right in with a question that really has life or death consequences. How on earth is it possible for two chemicals made of the exact same atoms in the exact same amounts to have completely, and I mean completely, different effects on the human body? Get a load of this. Over here, you've got cisplatin, a really powerful life-saving anti-cancer drug. And on the other side, transplatin. Now look at their chemical formulas. They are identical. One platinum, two ammonias, two chlorides. But one saves lives, and the other, it's not just inactive, it's toxic. So what is going on here? Well, the answer to that puzzle lies in this really fascinating concept called isomerism. Think of it as the secret key to understanding how chemistry shapes our world, from the pills in our medicine cabinets to the very stuff we build our world with. Okay, so what exactly is isomerism? At its core, the idea is actually pretty simple. Isomers are compounds that have the exact same molecular formula. It's like they have an identical parts list, but those parts are just put together in a different 3D shape. And that tiny, tiny difference in arrangement, well, it changes absolutely everything. Think about it like this. Imagine you have a sofa, a couple of chairs, and a coffee table. You can arrange them in a way that feels super cozy, perfect for conversation. Or you could arrange the exact same stuff in a way that's just awkward and totally blocks the flow of the room. Same furniture, different arrangement, completely different function. That right there is the heart of isomerism. Now, in the world of these coordination compounds, this difference in arrangement usually comes down to two main flavors. First, you've got the cis isomer. That's where two important parts are neighbors, sitting right next to each other. Then you have the trans isomer, where those same two parts are on opposite sides of the molecule. Kind of like they're sitting across a big dinner table from each other. To really get a picture of this in your head, let's strip it down to a super simple analogy using some building blocks. Okay, picture this. You've got some building blocks, 4 red ones and 2 blue ones, and you need to stick them all onto a central piece. You could put the 2 blue blocks right next to each other. Boom, that's your cis arrangement. Or you could place them on completely opposite ends, and that's your trans arrangement. See? Same blocks, same formula, but you end up with 2 structures that look totally different. Now, you might be wondering, okay, why did chemists even have to come up with this idea? Why is isomerism such a big deal in chemistry? Well, it exists because it solved this huge mystery that had early chemists totally stumped. They'd run an experiment and get 2 completely different things. Maybe one was red, the other was green, and they had different properties. They were clearly not the same substance. But when they analyzed the chemical formula, it was identical. Isomerism was that elegant aha moment that finally explained how this was even possible. Okay, let's put ourselves in the lab for a second and see exactly how this plays out, because this is where it gets really visual and, frankly, pretty cool. I want you to imagine you're in a chemistry lab right now. In front of you, there are 2 test tubes. One has this vibrant blue-green solution. The other one? A deep purple-red color. You look at the labels, and they both say they contain a compound with the exact same chemical formula. How can that be? The secret, of course, is revealed when we zoom all the way in to the molecular level. In that blue-green solution, those key bits on each molecule are arranged as neighbors. That's the cis isomer. But over in the purple-red solution, those same bits are on opposite sides. That's the trans isomer. And this just beautifully illustrates a core principle in chemistry. That tiny little shift in how the atoms are arranged actually changes the molecule's energy levels. This means each version, each isomer, absorbs and reflects light differently, which is precisely why our eyes see them as having completely different colors. Wild, right?
All right, let's ground this in a classic real-world example that perfectly shows just how much this simple little rearrangement can matter.
Okay, take this cobalt complex here. The formula is the same for both. But when the 2 chloride atoms are adjacent, in that cis position, the compound forms these really beautiful red crystals. But when those 2 exact same chlorides are arranged on opposite sides, in the trans position, the compound forms green crystals. It's the same set of atoms, but their relationship in space creates 2 completely different stable compounds. And this difference in geometry and shape isn't just some neat party trick that makes pretty colors. Like we saw right at the beginning, it can literally be the difference between a medicine that works and one that does absolutely nothing. And this brings us right back around, full circle, to our original puzzle with cisplatin. Why does it work? It's all because of its cis geometry. That specific shape allows it to bind perfectly to a cancer cell's DNA, kind of like a key fitting into a lock. This connection creates a little kink in the DNA, which is a signal for the cell to, well, to self-destruct. The trans isomer, with its different shape, is like the wrong key. It just can't fit into the lock in the right way to trigger that amazing, life-saving effect.
Okay, that was a lot to take in. So let's boil it all down to the 3 essential takeaways that will help you really master this concept.
So, what are the 3 key things to lock into your brain? First, the core idea. Same parts, different build, different result. Second, that mental image. Picture those 2 test tubes, proving that a simple shift from neighbors to opposites can totally change a substance's color. And finally, the life or death example, cisplatin. It proves that in chemistry, shape isn't just important, it's everything. The right shape saves a life, the wrong one doesn't.
Seriously, if you can remember those 3 points, you've really, truly grasped the core of what isomerism is all about.
So the next time you see a chemical formula, remember that the story doesn't end there. The real magic is in the architecture, in the shape. And that leaves us with one final thought to chew on. We've seen how arrangement affects color and medicine, but what else? What other properties, from melting point to how reactive it is, do you think are hiding in a molecule's shape?